Hello students, welcome back. Now let's go to section 2 of this notebook, hypothesis testing for population variances and standard deviations. Previously, we had been studying hypothesis testing for population means only, for known sigma, for unknown sigma, or for mean proportions. In any case, they're all means. Therefore, the central limit theorem applies, and thus, for sufficiently large sample size, we can use the normal curve, z-curve, and the z-table. What if we don't have sufficiently large n? Well, in that case, we may have to do some adjustment. If original population is normally distributed, then we can use adjusted one, t-curve, but still it was adjusted from the z-curve. So in hand-drawn picture, they're indistinguishable, and the techniques are exactly the same, or the table and the numbers are different. The hypothesis testing for population variances and standard deviations, on the other hand, they are fundamentally different. They follow, more or less, the chi-square distribution. Here are some chi-square density functions for selected degrees of freedom. 1, 2, 3, 4, and 5. So the sample size for this case is 2, 3, 4, 5, and 6. Because in one-dimensional case like this, the degree of freedom is n-1. As you can see, as the degree of freedom increases, the graph retreats to the right. And from the degree of freedom 2, the graph starts from the origin and goes up and coming down. In any case, we have to have the horizontal asymptote of y equal to 0 to the right. Also note that we only have the right-hand side because chi-square is squared quantities, so we don't have anything negative. And that makes sense because variance and standard deviation, they're all positive. You see, we had squared, so only to the right-hand side for variances, and take the square root of that, and that's standard deviation. Again, all positive. So we'll have to use these. How do we actually use chi-square? Well, let's begin from the structure of hypotheses. Here's the first case. Null hypothesis. Sigma is about the same as sigma 0. Alternative hypothesis. No, it's actually bigger than that. The other way around, less than that. Or the third case, they're just different. But then again, I cannot think of any good example for this, any kind of application associated to the third case. So I'm not going to discuss this one at all. Now for population means, this one made at least some sense. The two-tail test. Again, it didn't make much sense because we know the x bar value, the sample mean, and if the sample mean is greater than mu0, we get this. Less than mu0, we get that. Why do we set up just different? Well, think of this case. We have a number of sample studies, and we have several different x bar values. Some are greater than mu0, some are less than mu0. We have no control. So maybe we have to do this. But then again, if that's really the case, then probably this is much better hypothesis testing that we'll have to do. Data may be just too spread out. That's why we have so many different x bars flying around. And that's much better measured by sample standard deviation than several different sample means. See what I mean? That's one of many motivations of hypothesis testing for population variances. Of course, the other case is this, sigma less than something. But the third case, I don't see any importance there, so I'm not going to talk about this at all. All right, now that we talked about the structure of hypotheses and the theoretical background, chi-square curve, let's talk about how to apply. Well, here we go. We have these two important formulae. Variance, or excuse me, I'll be more precisely speaking. Population variance sigma squared is inversely proportional to chi squared if we know the sample variance s squared. Right? If this is known, then the numerator can be considered as constant, so we have inverse proportion. Now, on the other hand, if population variance is known, then this is constant now. In this case, the sample variance s squared is directly proportional to chi squared. So in this case, inversely proportional, so bigger chi squared, smaller sigma squared, smaller chi squared, bigger sigma squared. We have this inverse relation. In this case, no, they are direct. And we have to consider both, so this can be a little bit confusing. Now, for confidence intervals or confidence bound, I mean for those interval estimations, we didn't have to consider the second, just this one only, so it was less confusing. But for hypothesis testing, I'm afraid things are a little bit harder. All right, so much for all those, and let me copy and paste this thing for further reference here. And then let's go ahead with some example problems. Here is an example problem for confidence interval, but this one we covered in lesson 10. If you need some review, go ahead and review. Now let's go to an hypothesis testing example. You can stop the playback and read through the problem first. It goes like this. We have 24 measurements, no, excuse me, not different measurements of the same thing, but 24 weight plates of some weightlifting, and they have to be well balanced. For example, if left-hand side one is much heavier than right-hand side one, then weightlifter will have a hard time, so they have to be well balanced. But look at this. Some are as large as 27.9 pounds, much bigger than 25 pounds, and some is as less as 21 point something pound. This is outrageous. Looks like these weight plates are substandard, so whoever is making this must go bankrupt. But of course, this is a math class, so we have to actually quantify those and set up the hypothesis and test those. And that's what we are going to do. Let's set up the hypotheses. So is it going to be the first or the second? Which one? Greater than sigma 0 or less than sigma 0? Which one is appropriate? Well, first read the problem. There has been complaints. Yeah, there has been complaint about excessive variability. And read the problem. The variability is greater than acceptable standard deviation. So just by reading, it should be that. Another indicator is coming from the data set. Standard deviation of this data is 1.916 something, certainly greater than 1.0. So it should be this. And of course, sigma 0 value is 1.0 pound. All right. Now we set up. Now let's have some graphical description before going over to this. What kind of graphical description am I talking about? Well, null hypothesis tells me sigma is supposed to be about 1 pound. Okay, that's sigma 0 of 1 pound. So which one do we have to use? This or that? This or that? Population variance we're going to use is constantly 1.0. So it's going to be this or that. It's going to be the second one. So population variance is going to be directly proportional to chi-square distribution. So chi-square density curve, what does that look like? It looks like this. Forgive me of this lousy curve. Actually, this shouldn't go like to the left like that. Well, lousy graph. You'll see better graph shortly, so let's leave it there. And then we want (1.0) is what you want. And I don't know whether 1.0 will come here or to the left of mode, but it doesn't matter. It's not really that important. Key is this part. That is 5%. And we want this x value, the critical value, and compare this critical value with sample variance. What is sample variance here, by the way? We had sample standard deviation of 1.916 something. So square root of that is going to be the sample variance. So if the sample variance falls here, then close to null, so null wins. If falls over here, the colored part, then too far away from the null, so null loses. That's basically it. Because this graph is the distribution of sample variance, which is proportional to chi-squared. You see, this sigma squared is constant because I'm using the null 1.0 there, and then n-1, that too is constant, and we have 24 measurement, you can count, so that's 23, so 1 over 23, that's my proportional constant, and then s squared and chi-squared are proportional, so we have more or less the same graph, actually the same graph except for scaling. So we are in this kind of situation, and we are looking for the critical value. See the strategy? And understand why we are using the second formula here. All right, let's go back to the problem. Okay, here's the setup. And sample size of 24, so the degree of freedom is 23, and sample standard deviation that we are going to use later, and alpha is 0.05. By the way, we'll have to use sample variance, so this one squared is the quantity we are looking for because chi-squared is proportional to sample variance, so 1.916, this thing squared, 3.67 something. That's the quantity you're going to be using. So it's like this. And here's a question, right or left? Which one do I have to use? Oh, as a matter of fact, I already showed you the picture. It's the right-hand side we're using because we're looking for distribution of sample variance, which is directly proportional to chi-squared. So no inverse, so no flipping. It's the right-hand side. But if you get confused, then don't worry, just do both. 5% here, 5% there, and then do both. And if you run everything, eventually, which one is the relevant one will reveal itself. So don't worry, just do both. That's what I did here. So how did you get this and that? Well, let's go over to my chi-square table. And then the degree of freedom is 23. Yes, here, 23. And then which column do I have to look at? Let's see. We want 5% to the right and the 5% to the left, either way. So we have to look at 95, this one, and 5% here, those two columns. So at the degree of freedom of 23, we get this and this. 13.091 and 35.172. Which one is the one that we are going to be using? You don't really have to worry about it at this moment. All right, let's go back to the problem. So 13 point something, 35 point something, and then we'll calculate the variance values associated to those chi-square values. There you go, there's one, and there's two. Oh, I could have used variances without taking square root, but here I decided to take square root and then use standard deviation. That's okay too. So one is this and the other is that, and then observed standard deviation. The sample standard deviation is 1.9 something. So which one is the relevant one? Clearly it's this one, you see. 1.0 is in the middle, so this one is even farther away. So idea is this. 1.0, 1.23 something, that's a critical value, and sample standard deviation is too far away. So I'm going to reject H0 and accept HA. Final picture is actually like this. So chi-square value associated to the critical value is 35 point something here. And the chi-square value that you get from the observed sample standard deviation turns out to be 84 something, way, way outside. So reject null hypothesis and accept alternative hypothesis. You can clearly see that. That's a standard method. Getting the distribution around the null and then look at the variance of, look at the distribution of sample variance. That's the standard method. But after this video, we're going to talk about an alternative method as well. Some people may find that one a little bit more interesting. We'll see.